So good morning, everyone. You've made it to the end, as have I, as have all of us. And so we have a little bit left to cover on wireless, and then we will talk about kind of what the plan is from here. Monday's the last day of lecture, so this is our last day. And we will have our final I Show It coming up on this date and time. Let me see. That's for Tuesday, Thursday, 8:30 to 10. So we show it. I show it as Tuesday, May the 7th, from 8 to 11 a.m. in our regular classroom, SR1 130. I do need to verify the classroom time, or the classroom location rather, because Matthew was telling me in the department office that there's some stuff that's changed, but I believe we're rock solid on that. But I will confirm either way via email to you guys. Okay, so we have a little bit left to kind of cover. We're going to take a peek at the last half of Chapter 22 and then a little bit more on 23, just to kind of make sure we round things out on wireless networks. If we have time, we'll take a peek at a little bit of network security, but that's at least we'll have time to cover RSA, I believe. So the big problem with wireless in mobility is the fact that we're moving. The fact that it's wireless isn't so much of an issue. So there's a spectrum actually of wireless problems, if you will, and it depends on sort of where you fit in the spectrum. There's no mobility at all, where like at home on a Wi-Fi network, you can move around inside the house and you can associate with your SSID and go weak and strong and get closer and further away, et cetera. But as far as the network's concerned, that's not causing any mobility issues. It's just wireless. Mobile users connecting from the one Wi-Fi hotspot to the next and having to get a new IP address, that's a network issue. And that one is considered moderately mobile. However, there's a spot in between the two that would exist, I guess, maybe right about in here, where you are moving from one piece of network infrastructure or the other, but it's meshed, like with a wireless mesh network. And in this case, you don't change SSIDs, you don't change IP addresses, you don't have to read DHCP, but you are nonetheless moving from one piece of physical infrastructure to the other. So that one's kind of in between, and it does require some help from the network. It's not invisible to it. All right, and then finally, you have high mobility where, unlike with this middle one where it's okay if you disconnect your connections, you shut your laptop, you walk to Starbucks, you open it back up again, you expect to have to reconnect. With high mobility, usually there's a desire not to have to disconnect. So this would be driving across town while you leave, while you stay connected to a cellular network. Okay. Let me move us forward just a little bit further into this then. So for the longest time, there's been a protocol that lots of things have been based on in the future, like VPNs, for example, called mobile IP. And I can't ever decide if it's growing or shrinking in popularity. And I do need to do a deeper dive on sort of where we're at with it these days, because it doesn't seem to be disappearing. And in fact, it does seem to be remaining as a current topic in lots of lessons, lots of books. So we probably need to kind of fold it into our conversation a little deeper. But I'm going to give us a brief look at it today, since we don't have a whole lot of time to dive deep, and it's not really a class focused just on wireless anyway. So the idea behind terminology like mobile IP, it's a collection of tools, some of which run in the routers, some of which run on your desktop or laptop, that are intended to allow you to move around without requiring that the user who's trying to communicate with you do anything at all different. So the terminology introduced here is that while you're home, on your home network, you have a permanent IP address, or at least it's one that's from your normal permanent subnet. And the router that you connect to, if it's going to support this activity of making you mobile, meaning leaving your network without making other users realize it, it's going to have to participate by running some software called a home agent. And when you move away to someplace else on a temporary basis, maybe you're traveling, maybe you're at a conference, then the foreign agent software needs to run in the remote location. It can run in your PC itself. And you've got a pair of addresses, one that is still back at home, and then one, of course, that's assigned to you by the local network to which you've attached. And the idea is that there's somebody at the bottom, a correspondent, who wants to communicate with you, and you don't want to have to update DNS, and you don't want to have to teach them a different name or a different IP address. So you will let them continue to try to connect to you at your original home location, and the router will intercept this traffic and send it back to the location where you are. So they will continue to send traffic to the old location. It will pass through a tunnel over the wide area network and be either pass through that router where the tunnel's terminated, or if you're running like a VPN program, it would go all the way into your machine. So the user doesn't know that you're not there. Here's where mobile IP differs from VPN networks. In this example, what mobile IP, and it doesn't say mobile IP on this slide, but it is the name of the protocol that you're looking at on this slide. What mobile IP will do is allow the person that is being contacted, the traveling foreign agent, if you will, to communicate then directly back to the correspondent. So this is a little bit challenging, because if what the user is trying to do is, say, a TCP handshake, if you really don't want them to ever know any, if you don't really want them to know anything different about it, then they are going to require that the response to the TCP handshake request come from this router, not from someplace else. So that's challenging, and it's the reason why it would require a deeper dive and more time to kind of dig into that. But here's what I can tell you that a VPN does. A VPN is similar to this. And so I'm going to copy it over to my handy dandy sketchbook here, and we'll paste it in. What a VPN does is similar, except it doesn't ever correspond with you directly. And so we can just get rid of this line here completely. This one doesn't exist. And you will continue to communicate both directions here for the remainder of the connection. So there's usually a device here, or it could be integrated into the router, and it's called a VPN concentrator. And so what you are doing is maintaining this illusion that you are on the home network. So once you establish a connection, what's actually going on with the VPN software is you have your physical layer, you have your data link layer, you have the network layer, which I'll just write with IP, that is given to you by the local network. So this is so that the local network will continue to recognize your packets. But what VPN software does is it comes in here and inserts itself as a second IP layer. And so this is the one that the VPN layer does. And then above it, no one knows any different. So the transport layer sees an IP layer below it, and the application layer sees a transport layer below it. But these guys at the top think that their IP layer is here, and the guys at the bottom think that they are working with this transport layer up here. And so what the VPN software actually forces you to do, and the reason why it works so well, is it's taking anything your application sends, and this IP software is intercepting it, and it is forcing it over this internet connection to go back to one place on Earth only, and that's to the VPN concentrator. Once it's inside there, it can loop its way right back around, and using the IP address that you really want to get to, send you out to wherever you're really trying to get on the internet. And when people send something back to you, the VPN concentrator puts it back into this tunnel, and it sends it back to this IP address. So nobody on the network here needs to do anything different, because it looks like normal IP. Your PC has 2 layers of IP running, or your phone has 2 layers of IP running. And your app thinks that you're back at the home office. If you look at your IP address, it comes from the home office. If you start up your VPN, it will read DHCP for you, but it will DHCP over here. So it's very elegant. So it's very, very similar to this diagram. The only thing that we change is we get rid of this line that went through here, and instead continue the illusion. So mobile IP taught us a lot about how to build these things effectively. and that's why it's still in these books. But I think VPN is a little closer to what you guys are actually using and what you may be used to. So there's a few other variations of this that are shown in here in the book that we're not really going to worry about too much. And there's some other examples of where you can. This would be like a VPN where you'll anchor to somebody in a different location. All right, so I don't want to get things too confused here. That's what I wanted to show you out of that lecture and out of that part of the chapter. So let me move to the next one. Right? And this one we're going to talk a little bit more about how we manage things in cellular networks, and then we're going to switch over for the last part of things to security. So the idea of routing something to mobile is done through several phases. If it's a phone call, it's different than if it's data. So with the phone call, you go through the world's telephone network, which is called the public switched telephone network. Switched because every time you pick up the phone, you dial an address. You think of it as a phone number. I think of it as an address. And it causes the equipment to establish a non-shared, non-packet switched, constant bandwidth circuit between you and the destination. So in this case, the destination is a place in a mobile switching center where your phone number is parked. So it will receive the request from the signaling network, the SS7 signaling network, to say, I have a phone call coming in for a number that I show you are responsible for terminating. You are responsible for handling. And what the mobile switching center needs to do quickly is to pass that through to your telephone. So it switches network types. If you are traveling or remote, for example, it may end up having to go back through the phone network to reach wherever you are. So me in Mexico, for example, or something like that. But eventually, there's a mobile switching center that has visibility to your phone. The serial number and EIN number in your phone uniquely identify that handset on Earth. And wherever you are, your phone is announcing the fact that it's there. And this is how cellular networks then negotiate. And one of them chooses you. You don't actually choose it. It chooses you, and you establish a connection. And at that point, they look into a global database to figure out where that phone number was originally registered, and not so much in city and state, but with which carrier. And they'll see Houston Cellular is the ancient name of what is now AT&T Wireless in Houston. It went through several revisions, Houston Cellular, and then it went through Singular, and now it's just basically AT&T had another step in the middle there. But that's who owns the number. That's who shows up in that database. So there's a message that's sent from whomever this provider is back to your local cellular telephone provider to say, hey, your guy, one of your guys is on my network. And he's connected. And because you and I have talked before and we have a contract, and I will let him in as a roaming partner or whatever it is that shows up on your phone, then I'm willing to help service him. So make a note, he's in my network right now, and so if you have any phone calls for him, forward them to me. And so that's exactly what happens. So all this is going on. This registration takes place before the phone call can happen, but once you're registered, the phone call happens. All of this handoff happens within a moment, maybe a second if it's international, maybe a little longer. Then you notice the pause. It's longer than dialing a regular landline usually. So it will cause this mobile switching center to send a message to my phone over a completely different messaging protocol, and my phone will do whatever my phone does, play an MP3 file of a phone ringing or of a cat crying or whatever sound you've sort of picked, and it may vibrate. It will certainly activate the radios, and they will go to full power at that point. So one of the things this message does is wake your phone up, because it's always listening with these beacons for a message that says, hey, you've got an incoming phone call. And it's elegant, right? So your voice connection is completed. Whatever this person is saying is being digitized, sometimes at the house if you have a cable or a television service, high-speed internet, and that's where your phone's plugged into, then it's being digitized right there. Otherwise, it's being digitized back at the first building in the phone network, and it travels over one type of compression algorithm for compressing audio for voice lines. Once it gets to the switching center, it's very possible it will change to a different type of coder decoder algorithm codec, make its way to the foreign mobile switching center, the remote one, and at that point it will switch to a third type of compression and be connected to your phone call based in part on the number of users on the tower and the amount of bandwidth available per user. So when you talk back, your voice is encrypted by the phone and digitized by the phone and sent back over. So this connection is generally considered to be highly secure, and I know of no exceptions of where people have been able to break into the carrier's encrypted data streams. And you should always assume it's happening, but I believe it to be among the most secure connections of all. It's just not, partly because of the way they manage the devices. They don't even give you a place to even try to sniff it. All right, so that's what's going on with voice. What happens with data? And let me see if I can find the best slide that I like in here. They're talking about switching things around, but I want to get a little bit, I think I like this one. So what happens with data is very, very similar. With data, what's going to happen is you'll have radio that connects you to your phone handset again. But as soon as you get to one of these mobile switching centers, you're going to bail out of the public switch telephone network and drop instead onto the internet. Now, what's ironic is all of these towers for years and years and years have used, and I'll open this up because I'm going to go to this next and open this up. They have for years used IP to send everything from the bottom of the cell tower, simply because it's less expensive. So when they get your data signal and your voice signal, basically what they're doing is digitizing both of them anyway. I don't want to look at Hamming codes again. I don't think you guys really want to do that either. Here's the one I'm trying to find. Okay. So this stuff will all bail out onto the internet. They've been sending all of your voice messages between these mobile switching centers via IP in lots of areas for, I'd say, 10 years at least. Way ahead of the curve of the rest of the phone industry sending all of their calls via IP. The cellular industry was able to kind of leapfrog and look at that stuff that was going on. Okay, going to take a little side trip now to show you something that is available if you guys are interested. There's a very good book that talks about digital transmission, and it's called Communication Networks, and it's by Alberto Leon Garcia and Indra Wajaja. And it goes deeper into the electrical engineering part of what goes on with transmission fundamentals than our textbooks do, in particular, more than almost any computer science networking textbook does. But it also covers the basics of computer networks. This one's more concerned with more broadly communication infrastructure. So it's got some material in it that's terrific and somewhat unique. So I want to race through in 10 minutes, maybe 15, and walk you through a little bit about what's in this book. So they cover some of the basics about what digital transmission is, but they start to take an approach that might make a little more sense to some of you on how do we get data actually encoded and over one of these communication possibilities. And so this is part and parcel of what happens with wireless networks in particular. So if you only send ones and zeros, you can send two types of things at a time. But if you can find a way in your communication network to connote more than just two types of signal, and we'll take a look at a couple of ways of doing that with amplitude changes, for example, then maybe if you find a way to send 4 different signals, then you have doubled the amount of data that you can encode. So 4 different signals means each signal can be assigned 2 bits. So 4 signals I could cover. The first signal would be 0, 0. Maybe that's a high negative voltage. Maybe the second signal is a low negative voltage, and it could be represent 0, 1. Low positive and high positive cover out the other 2. And now for each pulse, instead of sending either a 1 or a 0, you can send 2 bits at a time. So we're all over this and finding ways of sending lots more than 2 bits at a time as well. So this has the ability of multiplying exponentially the amount of data you can send on the very same frequencies, on the very same type of radio network. What you need is the ability to get better at dividing. Instead of this, maybe you've got a way of doing signals that are this strong or signals that are this strong, and being able to put little bands around it. Presto, double the amount of data that I can send. So more bits means more content. There's two fundamental ways of approaching this. You can have blocks of data or streams. Streams are considered the types of packets that you produce for real-time voice or video, but this also includes data that's streamed digitally by radio stations where maybe it's not really even packetized, and at least not the same way, and it's certainly not shared. So there's no compression or contention along the way. All right, total transmission time. You guys have seen this plenty of times before. Distance of your network, the time it takes to transmit something, how long it takes to propagate across the network, et cetera. Compression becomes a big issue in this as well, and we will compress in real time data that's sent across. They take you through a little bit of video and walk you through the block information, and then they finally get to something that's kind of new. And this is an analog representation of a speech being encoded for real-time voice. And what they're basically showing you is quantization will take this analog signal and restrict you to certain key patterns. And I'm not sure it's totally obvious what's going on here, so I'm going to paste it over and point out a couple of little things here. So what I want you to notice is that every one of these places where the orange bar stops, it's perfectly touching one of these values on the left. So what they're doing is looking at your analog signal. They are at even time intervals, here to here to here to here. They are looking at which of these values on the left is it closest to. And sometimes there's a little bit of difference here. Here's a little bit more of a difference here. You've gone over maybe a little too much. But you know, there's a little bit of wishful thinking here as well. What if your time that passed where you're supposed to take your signal occurred right here? You know, would you pick this one or would you pick this one? You have to pick one of the two. You can't pick in between. So what you're going to accumulate over time is you're going to accumulate, starting with this one here, you're going to accumulate a series of values. And I had another 7 after that. I'm just going to write the top values now and forget the rest of that nomenclature. Then I have -1, -7. So what I'm doing is just reading these values here, -7, and this one's -5. So you're quantizing this down, it looks like, into 16 values from -7 to +7, but only the odd numbers. I'll forget the odd number rounding for a second. So this looks like a range of 16 numbers. So I could do this with 4 bits. So what I'm basically saying is, at every time interval, I have a network that can send 4 bits of digital information, and the 4 bits are going to tell me which one of these circled values the person's analog signal was at that particular point. And so you just send these in order as they go across the network. Now, you may have noticed that these things actually are skipping every other one, and therefore I really don't have 16, I have 8, so I can do this with 3 bits instead. And so the claim is, if you send me this string of data at the other end, I will rebuild a network, and I will do it by writing, making an exit 3, and then 5, and then 7, and then 7 again, and then 3 again, and then -1, and -7, and -5. And then I'm going to interpolate and draw a smoothing line over these things and try to get the same kind of graph. If I convert my digital signals back to an analog wave like this and play it with a speaker, for example, in your ear, you will recognize not only what the person's saying, but who they are. And it works. So for human voice, what the phone network actually does is they quantize to 256 levels, so they need 8 bits to get this done, and they do it 8,000 times a second. So it's a 64,000 bit per second channel, 64 kb per second, and just 256 values is plenty enough for you to distinguish between the voices of every person whose voice you recognize, and enough to know that somebody who's speaking isn't one of those people either. So it's kind of surprising that it takes so few differentiation points, but that's what it takes for you to recognize one person's voice versus another. So this kind of walks you through a little bit of that. They also give you some formulas to tell you, based on the bandwidth, based on the frequency of the network, how much data can you expect to send over it at a time. And it's basically double the frequency. So if it's a 4 kilohertz signal, then you can send twice that in samples. If it's a 22 kilohertz signal, then you can sample twice that rate and get an amount of data out of that. So they walk you through a little bit of that. Okay, so this gets us to, I'm taking pieces from sections of this book to kind of show you what's going on. So why do we digitize data? There's lots of impairments, and this lists out some that we haven't even talked about before, like thermal noise. The hotter it is outside, the harder it is for these networks to transmit their information. They gather more noise. The electrons are naturally vibrating at a faster rate because the temperature is higher, they're more excited. Those things generate electrical interference. They impede your ability. You also have impulse noise, which is a single pulse of something, somebody unplugging and plugging a wire in that's near you, or something passing overhead or underneath, and you've got impairments like that. So in the old days, what we had to do was repeat the signal. And so if you had a signal that was sent like this and it traveled for a while, it would get weaker. And when it came time for you to match it, I'm going to see how well this works. I have a feeling this will backfire on me a tiny bit here, because I think I know what the author actually did to draw this second image. But let's just play along and see. All right, so this is my original image. And after it's been attenuated, it's going to look different. So what will happen in a traditional phone network, excuse me, I got to mute. I had to sneeze, may have another one here. You will receive a much weaker signal somewhere along the way, and all you're going to do is re-amplify it again. So what I want to do is make this thing taller and taller, and it's going to be hard for me to do that without making it wider and wider. But what I'm going to try to do here is make this thing stronger. And when I do that, what I want to see is if this signal, if it looks anything alike. And they don't really. They look significantly different from each other. So let me move this thing back down. Here we go. No, still didn't get it. I want to try to at least, okay, there's that one. That's not the one I want. This is the one I want? Yeah, that's the one I want. Hope I got to get the right tool here. Okay, now maybe I can get these things kind of close to each other. So it looks like it might work. It's sort of close. But there is some difference, right? So this is below the line down here. There's been some noise introduced in that. So it's not, it's not exactly what I would call a perfectly reproduced signal. And this is reality. When you boost this signal, you just basically amplify it. You amplify the original signal and all the noise. Why? Because you have no way of knowing what part of the signal was good, useful voice and what part of it was noise. With digital transmission, what ends up happening is the same type of attenuation. You don't send a square wave. It gets converted to a sinusoidal pattern. And it has exactly the same problems. It has distortion, it has attenuation, it gets weaker, there's impulse noise, all those impairments that we looked at a minute ago. The difference here is I can still make out that this was above the line and was a 1, and this is below the line and was a 0, and this is still a 1. And so what I can do when I receive this is rebuild it new with no noise at all, regenerate a perfect signal again. So instead of repeating, we'll regenerate it. And this is the way telephone calls are sent as well if they are digitized, and they are all digitized long distance, except for lots of international calls like to Mexico are not, and you'll just basically rebuild it. All right, so how do you actually encode data on one of these networks? Here's an example of where I've chosen to encode my signals with a positive and a negative voltage. And it could be just as simple as that. But the problem is clocks need to stay in sync between the sender and the receiver, and we don't have perfect clocks. It's like two wristwatches if you've ever had a manual one, and you meet the person again the next day and you look and you're a second off from each other. Well, that's an example of the crystals that are in those clocks not being perfect molecular copies of each other. Right? The same is true in the crystals that we use in communication systems as well. So the problem is, what happens if somebody wants to send 1,000 zeros in a row? That's their data, right? So if they send 1,000 zeros, you're going to lose any ability to hear those intermediate pulses that normally would occur between bits when they periodically change from a 1 to a 0 or a 0 to a 1, which you can see happens in this graph. You'll lose all that, and you'll lose track, and you'll get off track. So one of the problems we have to solve with these is we cannot use that type of approach to send send data. So we can send a little pulse, and if it's super small, it's going to have kind of that bell shape. But basically what we're trying to calculate is how often can we do those pulses across a network. And Claude Shannon, who is an engineer for Bell Labs, calculated based on the amount of noise on a network how much you can transmit at any given time. So we looked a few slides ago that said you can send twice the amount of bandwidth based on the frequency of the connection, but that's impeded by noise, by all the things that we've just finished looking at. So noise limits your accuracy of the measurement. It increases the rate of errors, called a bit error rate, and it places a limit on the number of levels of amplitude that I can actually produce on my graph. So a minute ago I showed you maybe I had the ability to do 2 above and 2 below, and so I could have this be 0, 0, 0, 1, 1, 0, and 1, 1. And so if I sent a sine wave that looked like this, you would write down the data as 1, 0, 1, 1. This is supposed to be 1, 1. 0, 0, 0, 1. So that's my 8-bit byte, and I did it with this sine wave. But if you have a lot of noise and it's moving these signals up and moving these signals down, maybe you can't do 4 anymore. Maybe you only have 2, and so you're back to just 0 and 1 again. So that's reality. So an example here with lots of noise, where the noise is so loud it's close to the level of the original signal, then you're not going to be able to discern what happens, and as you can see here, you're going to end up with an error. So like I mentioned, Shannon had a formula for that, and if you give me a second, a friend of mine tells me they have 2 extra tickets to the Astros game at the club level. He's just going to kill me, so I'm going to say I'm in Mexico, so I'm sorry. Okay, I can't do it. So that sucks. He invites me to go see Astros, and I can't go. I'm a sports aholic, in case you haven't figured that out. All right, so what this basically says is you can take the bandwidth of the network, but you need to mitigate the rate down by a measurement of the noise. And at least it's a log of the noise. But what this basically shows you is that on a network where you've got 10,000 signal to noise ratio, which is great, you can send 45 kb per second on a network that's 3,400 hertz. So it's a direct calculation, and what this let people do was change the bandwidth on the fly based on the noise that was present in a network at a given time. Well, the phone company doesn't want to do that. They don't ever want to change the bandwidth because they're charging based on bandwidth. So what they will use this for is to test whether a network is being maintained properly within the allowable signal to noise range so that it can accurately transmit the service contracted. And they'll send people to fix and re-engineer and adjust it if it starts to drift off in a direction that's bad. So you've got these communication channels, and you basically show, just in general, based on practical experience, if you want to send a single voice channel, then you need the ability to send this many bits per second. On a copper pair can do this amount of frequency range. You should expect to get between 1 and 6 meg per second out of it. Coax cable can do a lot more than that. Optical fiber, 40 gig worth of wavelength over a bandwidth that's many terahertz. All right, so that's kind of what I wanted to show you in this. There's a couple of other fun things where they show how to combine signals and how noise can sort of reduce your number of divisions. I just talked about that before. There's one last thing I want to show you. It's a little repetitive in here, so it's a different. It's called line coding, but there's a little bit repetitive in different chapters. Okay, so here's a really important demonstration of the different ways we've chosen to try sending communication data over different types of network by changing how we code it. So the bits are the same across the top. 10101110. It's the same. Depending on the encoding mechanism you've chosen, the encoding algorithm you've chosen, you will represent those bits in different ways. Unipolar uses positive voltage for ones and 0 for 0. Polar non-return to 0 uses the opposite polarity for zeros and the positive polarity for ones. Non-return to 0 inverted or differential encoding flips the positive and negative polarity that it's going to use every time you go from a 1 to a 0. So you go from a 1 to a 0 here, and you go from a 1 to a 0 here, and you go from a 1 to a 0 here. So I'm going to start off with 1. Normally I would go down if it wasn't a 1, but because it's a 1-0 transition, I'm flipping and staying up. And then I stay inverted. So now 0's at the top and 1's are at the bottom until I have another 1-0 pair, and now 0's at the bottom and 1's are at the top. But I will flip and alternate for repeating signals as well. So what am I doing? Why do I have this crazy scheme to do this? It's to try to make sure I don't go very long without flipping from one polarity to the other so that the receiver can see my clock signal. That's the only reason I'm doing this. The problem is if you've got, it's still possible to have some strings that generate patterns that are not, perfect for keeping your clocks in sync. So the ones that we use on T1 lines are the ones at the bottom, Manchester encoding. And you can specify as a customer what kind of coding you want on your line. You can program the card in your router to do a certain type of coding. It's one of the things you get to choose in the card configuration. So the phone network will adapt, and they will use the encoding that you want. But most people use non-return to 0, B8ZS, and Manchester encoding. So sort of brings back a whole acronym soup for me. Let me tell you, that was a whole book's worth of acronyms. All right, so let's spend a little time wrapping up, talking about security, and then what we're going to expect to see on the final, and then from here for the rest of the homework that we've got. So we aren't going to have a final review today because I still have a class left to give on the other one, and I don't know quite how far I'm going to get, but I will give you guys a guide that will help us get the material in front of you need to study. The final will be based just on the homeworks that we've given in the second half, plus since I haven't had as many homeworks in the second half, there are materials that we've talked about in enough detail that I'm comfortable that if I tell you on the study guide and give you a practice problem and we look at the solution, I give you that it's fair game to cover. I will also hold any extra sessions that you guys may need if somebody wants to host another study session. We can do something like that. Or if you need a little 10-minute tutorial video, I can upload a short WebEx on a particular topic. So network security is really intended to kind of give us some structure. This chapter is intended to give us some structure on how to approach the problems that we've got with security. So generally, we're concerned about the network being up and available, that what we receive, we can have confidence hasn't been altered. Not so much that it hasn't been eavesdropped upon even, but no one's figured out a way to change it that we can't detect, right? That we know who it is that sent it, and that it's received only by the intended recipient. So there's ancient ways of doing this that have been around forever that change letters to others. We played with some of these maybe as kids as well. But this chapter goes a little more broadly than that. They talk about things like people in the middle that are intercepting the messages. One of the early attacks that was successful that caused us to randomize our starting sequence numbers for TCP, for example, was a replay attack where I would just sit where TrueD is and just simply listen to the packets going by, maybe with a Wireshark type of a tool. And then when we're done, I just take the packets that Alice sent and I wait a little while, and then I send them again to Bob in the same order, and I wait for Bob to respond, and he'll probably respond with exactly the same packets he did before, if it's a certain type of service, and I can repeat whatever happened. So maybe Alice was paying Bob money, and so I was able to just replay that and pay Bob twice, something like that, perhaps. So that was a vector of attack. There are lots of places where we will intercept and try and repeat things. Banking is a particular area, but that's why they change keys and renegotiate with every single connection so that replays just don't work. You can have people that intercept these messages, they impersonate who they are. We talked about that. Both of those are present in the example I just gave. You can have people that insert extra messages into a stream that don't belong. Adding more data points, for example, might sound innocuous, but it can be important. Denial of service attacks, we've talked about those before a bit as well. So what do we do to try and encode this? So what's crazy about this slide is they put in one slide something that's normally taught at least with 10, 15 minutes worth of material, and because it changed the world in 1979 when the paper was published out of MIT by Ravesh, Shamir, and Edelman, better known by their acronyms, by the first letters of their last names, RSA. And what they created was something that solved a really key fundamental problem that we've always had, which is the need for a separate second channel to send the details of how we're going to encrypt our data. So I have had in my career examples like a sheet of one-time passwords that I was to use to log in, and every time I logged in I marked one off. It can only be used once, so I didn't have to worry about somebody hearing me use the password, but I just had to keep the sheet secure. Well, needless to say, they couldn't send me that sheet over the network. That was the problem. So they have to mail it to me. When I worked at the student radio station in college, we got an envelope every month from the FCC that had a big orange, ominous-looking kind of orange-ready envelope and a folder, and it would open up, and it had a couple of code words in it that were the way you would know whether a supposed emergency broadcast, like from the National Weather Service with the storm alert, whether it was legitimate or not. And that's been all digitized now, but what would happen is you'd have a little weather radar radio or just an emergency broadcast system radio that every station had to have, and it would go off, and you'd hear a voice, and they would use these two code words, Alpha Bravo, for example, changed every month, and that way you knew it was legitimate, and you would make notes on whatever it was, or you broadcast it live, and then you'd repeat the message. So what I used to have to do was jot down where the storm was and try to remember it as much as I could, and then I'd hit a button that would play that crazy tone over the air, that you hear, and repeat it. Right? So that was an out-of-band password exchange. They'd mail me the envelope with the Alpha Bravo code in it, and then send me the message that I needed to repeat over the radio waves. They also had a little envelope in there that was to be opened only if a second set of codes was given that were printed on the front of this little envelope, as I recall. And inside that was a card with another set of code words. And if there was a national emergency, they would tell you to open that envelope, and then they would say the two words that were in that on the card, in which case you at least had a minute's head start to flee the city before the Russian missiles exploded. Right? So that's never used, but I mean, a national emergency only meant one thing. Everyone knew kind of what that meant. So again, out-of-band signaling, out-of-band password exchange. What happened in 1979 with Ravesh, Shamir, and Edelman is, and I'll show you the paper, and here it is right here. They came up with a way of exchanging keys over the network that required encryption. So over the very insecure network itself that they were using encryption to try and make more trustworthy, they figured out a way to exchange the passwords initially. So they solved the chicken and egg problem. And so the paper kind of walks through, and as you can imagine, like a paper would, lots of text. So I'm going to walk you through this graphically and show you what public key encryption really looks like. So let's say you have, I don't know what this red thing is here. It's kind of interesting. I kind of wonder if you guys can see it too. Okay. Let me turn that off. Where is it? I lost it now. That's what I get for undoing. Is it that one? Nope. Is it that one? It's that one. Yes. Okay, great. I have all these little hidden extra layers in here. Go figure. All right. Give me a new one here. You have Alice over here, and you have Bob over here, and they want to send a message to each other. So Alice can have a password that she uses where she passes her message through, and she gets an encrypted message out, and Bob receives the encrypted message, but he has to have the same function. So this is the out-of-band problem. How does Bob get this function with the key to decipher it? So what they came up with is a two-key system. So Alice now has a public key and Bob has a public key. And Alice also has a private key, and so does Bob. And they came up with an algorithm such that if you encode a message using Alice's public, well, let's make it private, Alice's private key, you're going to get an encrypted message out of it. And if you send it across the network to the other end, what Bob can do is take that encrypted message, which anybody can see, and use Alice's public key, which by its very name is public, and it will return the message back to M. So there's three things I want to try to accomplish here. I want to make sure that if I receive a message from Alice, that I know that it really came from Alice. So I'm going to ask myself the question, is it really Alice? And then the second thing I want to know is that only Bob can receive it, but I'm going to phrase that the same way. Is it really Bob? You know, in this case, it means, is it really Bob who can see it, for example? And the third thing I want to protect against is no eavesdropping, meaning it's okay if somebody actually sees the packets go by, but I don't want them to be able to decipher my message or do anything about it. All right, so which of those have I solved with this first example? Well, I would suggest to you that the only one that I've solved is that it really came from Alice, because anyone can see this message going across the wire, and they can use Alice's public key and decipher it. So it's not a message that only Bob can decipher, and it's also not a message that can't be deciphered, you know, can't be eavesdropped upon. Right, so I don't have any way of making sure yet that this is only something that Bob can look at. All right, what if I turn this around and I do it the opposite way? Let me pick another color here to do this. Let's pick blue. Okay, so I'm going to do almost the same thing. I'm going to take the original message. This time I'm going to use Bob's public key because as Alice, I have access to it. All right, so there's super lag. I hope you guys aren't hearing that too, but I can't. I'm moving my hand and the ink's not coming out at the same speed. So Bob can take this encrypted message, receive it, decode it with his private key, and he will get back the original message. So which of those have I handled now? Well, only Bob can get the message. Anyone else who eavesdrops upon it can't decipher it because they would need Bob's private key to do so. So if there were a way to combine these two things together, maybe I could check all three boxes. You know, that would be kind of the goal. Well, it turns out you can, and one reason you can is because, as you may have seen fly by on the paper there before, if you take a message and you encode it with one person's private key and then decode it with their public key, you're going to get the same thing as if you do it backwards, which basically means first encode it with their public key and then decode it with their private key. Those are opposite of each other, right? Public, private, private, public, and this should be an R. It looks a little bit like an E. So because those two things are true, it allows me to do a third option here, which is to encode the message, let's say first with Alice's private key, and then take that message. And so basically what I'm doing here is taking this and feeding it in as this input. So I have that input, and I'm now going to encrypt it a second time with Bob's public key. Send it across the network. It's some sort of permutated image, permutated message. And I'll do the opposite at the other end. So I'll take this doubly permuted message, and I will first decode it with Bob's private key and then with Alice's public key, let's say. All right, so that's the idea. So Alice encoded it, so you know that it came from Alice because only her public key will decode it. You've also used Bob's public key so that anybody that sees it along the way would need Bob's private key to understand it. And therefore, anybody who sees this message along the way can't eavesdrop upon it. All right, so this is really groundbreaking because what it allowed us to do was to use a single insecure network to have completely secure communications, including with people with whom we had never planned to have a communication before, like a website. So if I go to a web browser and I pull up a site, let's try like Amazon. I can't remember who Amazon uses. I may want to find someone different here. They may use themselves. No, they don't. Okay, good. So I clicked on the little green lock, and it shows this is a secure connection. And I can pull up the certificate for it and look at the certificate. And so basically what is happening here is that Amazon has gone to one of the trusted certificate authorities, a company called DigiCert Global, and they store keys. And they build a pair of keys like these public keys we've talked about for every one of their customers who's buying a certificate. So you can show up and you can pay them some money, and they will generate a pair of keys, and they give you one of them to hand out, and the other one they keep. So they encrypt a certificate for you that says, yes, it's really you, and they give it to you, and they say, send this out with all of your web pages. Anytime somebody wants a secure web page, I want you to take this encrypted version of this and include it with it. So when I make my connection to the website, I'm doing a few things. One of the things I'm doing is negotiating the exchange of a key through an intermediary third party. So I'll use what Amazon's public key is to decrypt the web page they're sending me. And that gives me confidence that at least no one can pretend that they're Amazon. But I send a copy of the certificate over to DigiCert, and DigiCert will use the data that they've got stored to confirm for me that, in fact, the key that was included is for the URL that I just loaded, so that it's really Amazon. And if that happens, then I will get, and depending on the browser, another little color of icon in here, or some sort of a green lock in most browsers. So that's what's going on with these things, trying to secure our connections. It doesn't work quite the same way with web browsers because you don't really have a public key that you give to the website to use, but you negotiate one at the beginning of the connection. Wireshark normally can't show you secure data that's being sent. So if I try to pull Wireshark up and try to grab a little bit of data from a website, for example, here's my Ethernet, and I'm going to go back to my web page, and I'm going to start my capture, and I'm going to reload this page, and I'm going to let it load, and then I'm going to stop the capture and search for HTTP. Is it going to give it to me? I sure hope so, because I definitely did it. Did it not? Huh. Did it connect with HTTP 2? No, it didn't do that either. How strange. Oh, there we go. It's doing something weird. Yeah, I lost my X in there. Wireshark's having a little bit of problem. So here's a piece of the data, and here's one of the reasons why I'm having trouble kind of deciphering what's going on, because this may be connecting to the web server, but in this case, it's encrypted. It's a secure website. You can see the green lock up here in Google. So what the TLS algorithm uses is port 443. And since we talked about VPNs a little earlier, I'm going to take the opportunity to show you a little something extra here. So normally what would happen is I would have my physical and then my data link layer, or my peta link layer if I don't know how to spell right, and my network, which is, I'm going to put IP down here, and I'll have TCP up here. And I would normally have my application hand things directly to TCP, but since TCP and any other layer in this doesn't really do encryption, I'm going to attach SSL, or current version of it is this encryption protocol called TLS, and it's going to insert itself in between. So the app is going to try to talk to port 80. This will intercept it, encrypt it, and send it to port 443. Because if I were to continue to send it to port 80, the receiving side at the other end is not going to know how to decipher an encrypted HTTP request. So what sending it to port 43 will do is send it across the network over to a waiting TLS program at the other end. It will receive data at port 443, decrypt it, but inside the computer, send it up to the app listening on port 80, which is my web server. So the encryption and decryption happens safely inside the computers at each end. The only thing that ever hits the network is traffic between ports 443, and so it's secure. But because it's encrypted and Wireshark is watching for stuff down here, by the time Wireshark sees it, it's too late. It's already been encrypted, and I can't make any heads or tails, out of the data that's at the bottom of this thing. So if I move this up a little bit, let me see if I can get this to move. This is all in ASCII, and it looks just like gibberish. I don't really have any idea what any of it means. Whereas if I were to connect to an insecure website or one that's not encrypted, I would be able to read it. Turns out, if you guys are ever interested in doing this, you can run a command line version of Wireshark called TShark. And TShark can do some things that the GUI version can't, like pull in extra files and pull in extra configs. And if you Google out there for how to use Wireshark to decrypt a TLS stream, it will give you a command that will run in Unix, and I think they've got versions for Windows as well, that will cause you will initiate your browser from the command line, and you will give it the URL that you want to connect to, knowing that it will be a secure connection, but you will put a parameter in the startup message for the browser that will ask it to write a copy of the keys that it's using, that we've just learned about, a copy of the keys to a file that Wireshark can then use to decode your messages. So you can look and see, if it's your computer, you can look and see what's going on inside of one of those streams. So it's kind of cool. There's a lot of stuff you can do with the command line version that is not as elegant as the GUI, but more interesting for sure. All right, so we don't need to walk through a ton more of this stuff. I will show you a few other things. There are some other household name popular encryption technologies out there, like this one, DES. It's not one that we use much anymore because it's not considered to be strong enough. But basically the way this works is you use a 56-bit key and run it through a key generator program. It cranks out 16 48-bit keys, and each of those is used to get an encryption algorithm going that takes your original data and then basically runs through 16 times through this and cranks out output. It's fast, so it works. It certainly meets a needed requirement that way. It's speedy, but it's too easily cracked. I found this interesting spreadsheet on Stack Exchange. It's actually a Google sheet, and I moved it into Excel, and you guys can find it out there as well. You're going to have the video, but you can take a snapshot if you want. But fortunately, the URLs on Stack Exchange are not bad. So what this basically showed was if you tell me the cost of electricity, I can tell you how many decryptions I can do for how much money in a second and in a year. So the point of this was, if you use a key that is 73 bits in size, which is bigger than the 56 that we just looked at with DES, you need 2 computers, 2 modern servers, at a cost of $1,000 worth of electricity to brute force attack your encryption algorithm. And brute force simply means try every possible key until you stumble across the one that they used and decode, therefore, the message. If you use an 83-bit key, you need a couple of thousand machines and $1 million to crack it in a year. With $1 billion and a couple of million machines, for billion for electricity, a couple of million machines, then you can crack a 93-bit code, and that's maybe like the Russian government or something maybe. And with a couple of billion machines and $1 trillion, you can crack 102-bit codes, which might be something like the United States government might try to pull off. So why don't we use 1,000-bit keys? I mean, if it's so easy to get these short ones, why are we using ones that are toying around with this number range, 128-bit keys, for example, for AES and others? Why not use 1,000-bit keys? Because it takes that long to decode. It takes longer, not that long. It takes longer to decode the messages as well. So if you stick your credit card in the card reader at the local grocery store, you don't want to wait 30 seconds to 3 minutes for the decryption algorithm to say that yes, the 1,000-bit key on this card, which was used to encode their credit card number, does in fact match the credit card number when I decode it with my half of the key. Nobody's going to want to do that. So there's a balancing act that goes on here. So it's kind of a crazy calculation. It's kind of fun to do, and who knows if it's completely accurate or not. But they basically calculated how many decryptions a machine can do, a fast computer can do with the best algorithm that we've got, and what it's going to cost you. So it's a very different way of proving the security of an algorithm from just proving mathematically that it can't be done. What this basically shows is that you can stumble across, if you're super lucky, and in the very first calculation, guess the key they used. But generally speaking, it's not an endeavor that you want to try and pursue because it's too hard. It costs too much money. Nobody's got that number of machines hanging around handy, right? However, there are countries that are building chipsets, including Russia, that have nothing on the chips but hardware SHA-256 encryption decryption modules to do orders of magnitude more of these in an hour than we could do with any general purpose Intel-based system. So you should be nervous about it. All right, fun thing to talk about that I don't usually get time to, but I will mention it for us. Kind of a pet peeve of mine. So let's say this is the world of all of the possible passwords that you could possibly use to log into a system. if somebody gives you rules other than please try to make the password harder to guess, if they give you rules like it must include an uppercase character, well, I can go to this sphere of all of the possible passwords, and I can now mark off my list of the ones that I need to try checking to see if it's yours, all the ones that have one uppercase letter. And if they also tell you it needs to have a number in it, then I can mark off all the passwords that don't have a number. And I don't even need to bother checking those anymore because you've just told me that those can't be your password. So as a hacker, I like this information because you're narrowing it down. All the passwords that are less than 8 characters or more than 20 characters or can't have a comma, space, or an asterisk, but must have maybe an ampersand, a parentheses, or a bracket. And this isn't to scale, obviously, but all you're doing with these rules is making life easier on hackers by reducing the possible set of passwords or values that they would need to check. So the word I'm looking for here for this approach is stupidity. And please do not participate in a scheme designing something like this for a company or prolonging this insanity, because it's not making people more secure, it's making them less secure. So yeah, if people are using dog or cat or password as their password, then maybe you should put a message up like Google does now, which says basically, please try to make your password harder. And not tell you it's got to be this many characters with this, got to have these, got to have that. And what I use is a password protector. So you guys have probably seen me log into this and when I'm popping into WebEx. So if I type in a site, for example, this one happens to be, I think, a relatively popular one. But if I go into something here like, WebEx, let me see if I can pull this thing up here. What I find are a few sites in here, right? And the password is hidden. I can generate a new password. So if I want to build a new one in here, we'll call it test site. And I will generate a new password for it. And I can make it as long as I want with numbers and characters. You can see it here, and I can save it. And so now if I come up here and say test site and pop the stuff in, test site's in here, then I can come over and paste it wherever I want. So I don't even know my passwords, and I keep my partner's passwords in here as well. I keep some of my mom's passwords in here just to keep them from using crazy ones themselves. So if you're not using a password protection program, then you're making life needlessly hard. So if you're using the same password everywhere, it's probably a bad idea to do it. There are a couple of sites out there you can go to, type in your email address, and they'll tell you if passwords for that email account have been found for sale on any of the underground sites. And that was in Wired Magazine, I think, a month or two ago. You can go look for that. All right, guys, it's been a fun semester. Networking's my entire career, basically, moving more into security. But I hope you guys had a good time in the class. What's going to happen from here, if I'm truly correct, and this is our last lecture, like I think it is, then the next thing you'll hear from me is a study guide, and I will give you some more problems. I don't know if they'll be in the form of a homework or not, or if they'll just be practice problems for you guys to kind of crank through. And I'll see you during the final. I'm going to ask the TAs to come up with a list that will allow people to swap times, because a lot of you guys want to swap from one to the other, but you can't do that without permission. And what I don't want you to do is to bombard me with requests. So I'll have a list, and what I had to do last year, it got really ugly because people didn't ask and sort of ruined the midterm experience. So I ended up coming up with a sign-up sheet that made people sign in when they showed up. And if you aren't on that sheet and there's not space, then I'll call your name out and you'll leave. So we haven't had to actually do that, but the rooms are generally at capacity. Matthew in the computer science department tries to put me in he usually has to change my class assignment a couple of times every semester because they fill up. So I don't know if we have a lot of extra space. So please wait until you get something. I'm going to ask the TAs if they'll put something together. I will also look to see how much space I do have, and if I have like 30 extra seats, then like no big deal. But you do need to come to the section that you're assigned to unless you have permission. I've already given some people permission for special circumstances they've asked me about, and those are okay. You're good. But anyone else beyond this point, we need to kind of do it on a sign-up sheet basis. All right, guys, have a great one, and I will see you soon. And if I don't remember to say it then, have a great summer. All right, bye, everyone.